I'm Kurtis Heimerl, as mentioned, a PhD student at UC Berkeley, and this is Expanding Rural Cellular Networks with Virtual Coverage. We're going to talk today about something that's not commonly talked about at traditional networking venues, and that's cellular networks. Cellular telephones are one of the most impactful technologies in the last 100 years. The amount of adoption is really only rivaled by the light bulb. 5 billion users in about 25 years. The first cell phone network opened in Finland in 1991. And there's been numerous studies showing the various benefits of this technology to users. But what you'll note is that 5 billion is not the population of the Earth. There are billions of people not on this network still. And some of these are Luddites, people with landlines who refuse to participate. But there's at least 1 billion people who just don't have coverage right now. And so this leads to the following question of, why don't they have coverage? And the answer is primarily economic. My own experience in many parts of the world says it's about $500,000 to $1 million to install a cell phone tower in a rural area. And what this means is that they need a dense population of users underneath that to pay for the install of the tower. So when you get to a certain low amount of density in a very rural area, it ceases to be economically feasible to have a tower there. So why are these towers so expensive? It turns out to be power. The GSM Association says that 95% of the people on Earth who don't have coverage live in areas without grid power. So these are highly correlated. And the International Telecommunications Union says that about half the cost of running a cell phone tower is power related. So the goal of this work is to reduce the cost of a rural cellular installation by reducing the power draw of the cell phone tower. So our plan is to just find the piece of a cell phone tower that draws the most power and find a way to cut it. So let's start talking about what a rural cellular tower looks like. This is a tower in north of Pakistan. And a rural cell phone tower, actually most cell phone towers, have about 3 parts. Here we have the base transceiver station in this wonderful shack here. This is the sort of brains of the operation, does the encoding of signals. We have the backhaul network, which obviously connects the space station to the rest of the world, so you can talk to your mother or whatnot. And then nestled back there, and it's very hard to see, is the power. There's a little diesel generator under that wonderful roof powering the whole unit. So let's go a little more in depth into these 3 pieces. The most common thing you might think of when you think about a base station is one of these. This is a Nokia Siemens BS240. Big iron solution to the problem, $500,000 to $100,000 a kilowatt of power, sits inside that shack, providing hundreds of calls. There's a couple interesting things going on. One of these is the open hardware. So this is a software-defined radio that you can actually use to build your own base station. It costs $2,000 to do that, and it'll only draw about 150 watts. The problem here is that the actual power, or the quality of the GSM signal is quite low, so it's hard to build a real network out of these. But there's a couple people, Range Networks is one, and I should say I'm employed by them, who have started to commercialize these technologies. So this, at this point, is $15,000 to build one of these base stations. And this is going to provide a high-quality experience for the users. For the backhaul network, obviously, you'll use a wired connection if it's available. But again, you're in a rural area. There will not be a wired network. So instead, what you see are these high-gain microwave links. So this is an Alcatel-Lucent MDR8000. So this is very high bandwidth, about 300 megabits per second. Costs $25,000 and consumes about 70 watts. It requires a spectrum license so that nobody's stepping on each other's toes. They're all very, very particular about their spectrum in the GSM world. So that's the sort of classic answer. And again, if we move to the cutting edge of what's going on, are these low-cost Wi-Fi links. So this is Ubiquiti M2, much lower bandwidth, but again, if you're handling less users, you don't need that high bandwidth anymore. At this point, you can get $100 and about 5 watts to backhaul your base station. And then lastly, we get to the power piece. So grid power, again, you'll use it if it's available, but it's not available. It's part of the definition of being in a rural area. Instead, what you have are diesel generators and batteries. And it's not necessarily even the cost of the generator that's the problem here. It's the fact that you have to build all of this related infrastructure to run one of these. You'll need to actually build a full road to be able to truck diesel into this generator and power it. And then you need to build a fence around that because diesel is incredibly valuable in rural areas. So these other costs start to spiral up until the whole install for power is $50,000 itself. So obviously, as you go to the cutting edge, we're trying to move towards renewables. And this gets away from a lot of that related infrastructure. You just put it down and it runs. But the cost of the renewables actually depends on the power draw of the base station. So let's do a little thought experiment. We're going to take the most cutting-edge base station that you can have, a range network 5150 with a ubiquity nanobridge connecting it. This is the lowest power, lowest cost base station that you can get. To power one of these for a week, assuming inclement weather, will require a kilowatt of solar panels and half a ton of batteries. So that's $15,000 of equipment itself. So this is half the capex of one of these towers, and that's just in equipment. It's not talking install. Obviously, hauling half a ton of batteries to a rural area is going to be difficult in and of itself. So this is still a huge problem. So how do we begin to reduce the power draw of the actual base station, which was the only piece consuming any reasonable amount of power in that whole story? So now we need to look inside of a base station. This is my range networks box that I shoved into a weatherproof box for tree mounting. You'll see there's three important pieces. There's the central processing unit. It's just the brains that does the encoding and decoding. There's the radio, which actually pushes stuff out over the air, and that consumes about 15 watts. And then there's the power amplifier, consuming 130 watts. So the story here is that if we want to be able to save power in this unit, we have to touch the power amplifier. This isn't something where we can make a change, a simple software change, and solve the problem. The thing here is that that power amplifier is going all the time. This isn't Wi-Fi. There's a beacon channel that in the GSM spectrum where that tower is constantly beaconing its location, who owns it, and how to connect to it. So that 130 watts is a constant power draw. So we're kind of in a rough spot here. We need to be able to touch that power amplifier. That power amplifier, as I said, draws almost all of the power. It determines the coverage radius of your base station to a certain point. Wireless is, bidirectional, and so eventually the power on your handset will be the limiting factor. But at 10 watts, after 10 watts, the power doesn't increase the range of the tower anymore. What you use that extra power for is actually capacity. So what they do is instead of, if you have extra power on your base station, you just transmit on multiple channels and to be able to handle multiple calls. The point of this slide is just to say we cannot use a smaller power amplifier. You've heard of picocells. They cover the area of a room, but we need to cover a lot of people to pay for this investment. So we need a macro base station, and the minimum size of that is a 10-watt power amplifier. Otherwise, we're going to limit the range or capacity of the base station, and we'll do so permanently. So how do we begin to do this with a macro base station? So yes, how do we lower the power amplifier power draw? We actually do something very similar, or very simple, and something used all over computer science and pretty much everywhere. We just turn the power amplifier off when we don't use it. This is our addition here, virtual coverage. So here's the story. You can see my wonderful diagram. The dotted line is your coverage. Happy smiling people are happy smiling users. And in the center is my base station. So in a normal base station, people sit in coverage and they make communications, lightning bolts being communications. But a lot of the time, there's simply nothing going on in the network. So if it's at the middle of night, you're just sitting there broadcasting that beacon channel, spending 130 watts doing nothing. And this is exacerbated in rural areas where there's very few people. And so there's actually very little communication going on. So most of that power is wasted. In virtual coverage, what we actually do is when the network is idle, we just turn it off. Turn off the power amplifier. And then if a user wishes to communicate, they just send a burst to the base station saying, hey, wake up, I need to call. Then the base station turns itself back on, or turns the power amplifier back on, and the users are able to communicate until, again, the network is idle, and it goes back to sleep. So a key point here is that because we are the base station, we can actually programmatically control when it turns on. So for instance, if we have a call that we want to connect to a user, we just turn it on and send them the message. So it's all very conceptually simple. So how do you begin to implement this? For the hardware, what we've done was we've added, you can see it in the upper right, a little hardware switch, which allows programmatic control of the power amplifier itself. A byproduct of this means if there's any communication on the base station at all, we're going to actually have 100% utilization of that power amplifier. It's totally on or off. And then there's a couple changes to the software of the base station. Now it listens so that if it's in idle mode and it receives a burst of a certain power, it'll turn itself on and exit that idle mode. So this is the base station side, conceptually pretty simple. The user side is actually much more difficult because now we have to have a mechanism for the user to send a wake-up message to the base station. We have two answers to that question. The first answer is this wake-up radio. This is an autonomous standalone radio which just produces this wake up message. So you walk up, you hit this button, and the base station turns on, and you get signal on your handset. The way that GSM works is that your phone is constantly scanning the entire GSM band. And if you have a quad band phone, this is an enormous amount of spectrum. So that can take up to 40 seconds for it to find the base station that you just woke up. So you press the button, you sit there, and you wait until your handphone gets signal. We did some tests. It's an average of about 25 seconds, so it's not too bad. We envision two ways to use this wake-up radio. The first is if you're in a relatively affluent area, like the North Dakota or something. Each user could buy one. They're only about $10. It's very cheap. All it does is produce signal on a certain frequency. If you're in a less affluent area, we imagine something more like a phone booth, where it's in the center of town and people walk a short distance to get coverage. And they're still able to save power in the network by not wasting all that power with the power amplifier. So this is just the first answer, but we can actually be more clever. So this is Osmocom BB. This is the open source GSM handset. In this, we actually modify the GSM protocol to support this idle mode. So at this point, what we do is the phone actually sends the wake-up burst itself. And then because it knows which tower it's waking up, it can connect immediately instead of scanning the whole band. So at this point, you have the handphone in your hand. You try to dial a number. You see no signal. You dial a number, hit the call button. It sends the burst to the base station, who wakes up and starts broadcasting the beacon channel. The phone immediately scans that beacon channel and connects to the base station, and your call goes through. So this adds 2 seconds to the amount of time for your call to go out. It's relatively trivial. If that base station is unavailable, it just moves on to the next one in some list of base stations you've scanned in the past that you know support this protocol. So that's outgoing calls. Incoming calls, like calls to the handphone, are actually relatively simple because, again, we control the base station. So a call comes into our base station, and we immediately exit idle mode. Then it's just a question of how long until the phone attaches to the base station, because it's constantly scanning. So again, with a legacy phone, what will happen is the phone will scan and eventually attach, and then you just connect that call to that user once they're attached. Again, with that being 25 seconds, maybe we put that user on hold, maybe they hang up and we call them back, one of those things. With our modified phone, we're able to be a little bit smarter and scan the known bands of towers that support this nearby more often. So then it's a worst case of 7 seconds, and it's still about an average of 2. The fundamental thing we're doing here is we're involving the users in the power provisioning of this network. We've done prior work in various places in the world, primarily Uganda, demonstrating that users in rural areas know a significant amount about their networks. They know where coverage is, when coverage is, and how to get it. I have stories of people climbing trees to get cell phone signal. I have stories of people hiking 3 miles up a hill to get cell phone signal. I have people telling me there is a spot of signal 200 kilometers down that road, and it's just this network. The amount of knowledge in these areas is amazing. And so the amount of difficulty installing a button in the middle of town it's very low. People will do it without a problem. At least that's our expectation. So there's a lot of technical details I'm skipping here. GSM is an enormous protocol, and so I didn't want to go in too much depth. But if it's interesting to you, come to our demo or read the paper. So let's start to measure the actual power savings. On the left, we have that thought experiment we had earlier with $15,000 worth of power equipment. And on the right, we have our base station with virtual coverage enabled. So this base station is now, we're assuming it's 100% idle, which is a little bit silly. That means there's no communication going on. But what it is an effective lower bound on the amount of power we can save, because this is exactly equivalent to a base station that has no power amplifier. This is just the CPU and the radio broadcasting. So we cannot save more power than this. And that is 84% power savings there. So here's a graph of the amount of power the base station uses depending on the idleness of the network. You can see on the top, the red line is a traditional base station, then we have our virtual coverage one. So what we've done is we've actually implemented a power proportional base station, so that at this point you only need the power, or at a 50% idle base station, you only consume about half the power of one of these original base stations. Because battery power is actually directly correlated with the amount of infrastructure you need, we're actually Capex proportional as well. So this means that a rural entrepreneur who wants to install their own base station now only needs to install enough equipment to run it at their own utilization. So if you are installing in a rural area where there's not enough users to have more than 20% or 80% idleness, you only need to install $4,000 worth of equipment instead of $15,000 worth of equipment. So that reduces that Capex cost significantly in these areas that we're trying to target. Unfortunately, what we don't really know what the idleness is going to be. And so that's really the next question. How idle are these cellular networks? Now, we have a little bit of a chicken and egg problem. We're trying to bring coverage to areas where there is no cell phone coverage. And so there was no way for us to know how much use there would be in those areas. Instead, we have a proxy measurement of 1 week of call logs from 2 nation-scale telecommunication firms, one in South Asia and one in sub-Saharan Africa. And these are those results. On the left of this graph, on the y-axis, you can see the idleness of each network. And on the x-axis, you can see the number of calls per base station. And yellow is day and night, and each dot is actually an individual base station in that network. There's 5,000 in South Asia and significantly less in sub-Saharan Africa. The first thing we want to note is that there's a sublinear relationship between these two variables. This is actually pretty intuitive. The calls will overlap, basically. But this, in combination with the linear scaling in terms of Capex cost, means that each user we add actually causes less infrastructure cost to the provider, which is great. This is, again, another benefit for rural entrepreneurs. The second thing to note is that there's a lot of idleness in this network, and these are real networks in the real world. So 86% of the towers in South Asia are more than 20% idle, and 53% for sub-Saharan Africa, which is a much denser country. So there's a lot of available power savings even in these real networks. And lastly, to reiterate, these are real networks. These are networks designed for high utilization. These companies installed these towers because they thought they were going to make money. We are covering places that they do not think they can make money. So our utilization will be even lower than these ones. So now what we're going to do is we're going to combine those two graphs to generate the amount of power saved in the network if they use the virtual coverage. And here are those measurements. If you had virtual coverage in our South Asian network, you'd be able to save 28% of the power draw over the span of a week, which is, I believe, 70 megawatt hours. This is relatively large. And if you just work at night, which is really when you want to save power if you're doing renewable energies or solar, it's up to 34%, and 21% for sub-Saharan Africa. So these numbers are high, but not enormously high. But, you know, hey, we win. So 28% for existing networks. This is effectively a lower bound for us on the idleness of our networks. Because if you could build a tower that had only 20% idleness, you would. And there's no tower there. So the question is really, what is our expected power draw in these areas that currently don't have coverage? And we think at least 60% idle, which is 50% power savings. So our goal was to reduce the GSM base station power draw and to reduce the total cost of a rural installation. And I think we did that. Virtual coverage reduces the power draw of a base station by up to 84% with an expectation of at least 50%. So in conclusion, we have virtual coverage, which is when we involve users in the power decisions of the network, and we introduce this GSM idle mode to doing that. We have these micro benchmarks, which show that our base station is power and Capex proportional. And then we had these macro benchmarks, which show that there's a lot of idleness in real cellular networks, which would cause an expectation for a very large amount of idleness in areas that don't currently have coverage. We've actually deployed this. These are a bunch of installations we have in rural Papua, Indonesia. It only started recently, so we don't have data yet, but it's part of my village base station thesis. There's 3 wake-up radios. On the top and on the left, those are installed in the local markets, or in these kiosks. There's sort of shops owned by people, and then there's one in the communal market. So I'm hoping it's going well. We'll see when I finish with this talk. I'll go look at the data. We have a demo in the demo room at 6, and I invite any questions. Thank you.
Hi, Alex Schnur in UC San Diego. Really cool. I have 2 questions, both based out of ignorance, one technical and one business.
Sure.
So the technically ignorant question is, at least in Wi-Fi, which I know a little bit about, scanning is an extremely power-hungry activity. Is that not true in cellular? Or if it is true, how does this impact the power consumption of the handsets?
It's actually a really interesting question, because when I originally brought this up to my GSM people, they were like, yeah, that'll probably be a problem because the handset off of network is going to scan a lot. It turns out that even when you're on network, your phone is constantly scanning for other networks to jump to give you better signal. So there's not a huge loss. The spot where you have bad battery performance is on a fringe network, where basically it's sending its broadcast at full power and the base station isn't receiving it. And so it's resending that message over and over. So this is not too bad from at least from our measurements and from sort of thinking about it through the GSM space.
Okay. And then my second question, which I'm sure you've thought about since you're actually trying to do this for real, is in your diagram of a rural base station. In my experience in sub-Saharan Africa, you were actually missing a very important fourth component, which was the armed guard. And while diesel, as you mentioned, is very, very popular, I imagine solar generators would be equally popular for a lot of the same reasons. And so to what expense is the actual OPEX dominated by fuel or the installation, and to what expense is it actually contributed by the ongoing security and maintenance of this infrastructure?
So like I said, the fence is technically Capex, and we had that one ITU measurement where 50% is power. Now, you're right that solar panels get stolen all the time, and what we have in our installation in Papua is literally everything is up a tree or under in a locked room because we're working with a school. So you're right, and there's a certain amount of this that you can get away with and a certain amount you can, and a certain amount of engineering that depends on the location. But at least for the diesel ones, the diesel is definitely still the primary cost. As you, I'm sure are aware, labor is incredibly cheap. So armed guard is not that expensive.
Rajesh and Stella from Facebook. How does so you talked about cellular networks. How does this work with, let's say that you wanted to provide some sort of internet connectivity to these kind of things? Can you use a similar type of setup to, or is it actually even cheaper to do things like voice over IP and different types of things besides cellular?
I have backup slides.
Okay.
I love it when I have backup slides for something. Yes, absolutely. So fundamentally, there's no piece of this that is about calls. You can do this with anything. You could wake it up and check your email. But the fact is that both email or data and SMS are primarily asynchronous communication methods. And so what can happen is that it just syncs as other people wake up the base station for their calls. And if that doesn't happen all the time, we instead wake the base station up every hour just for syncing purposes. So there's a lot of games you can start to play. But I will tell you that in my experience in the developing world, there is very little data use. SMS is, of course, popular. Our network in Papua is actually SMS only right now, and we're still using this stuff. So it's an interesting question and something I think we're going to look at more as we go forward.
Thank you.
Hi, Josh Reich, Princeton University. Love the talk, love the work. Two potentially related questions. The first is, I'm wondering if you guys have thought at all about potential attacks. I can imagine in some rural areas, right, you want to ruin your entrepreneur rival or disrupt the telephony network. I've got a little box, I just keep waking up the station and burn all of its power. So that's the first one.
Yeah, so that's actually addressed in the paper. We thought a little bit about this. This is like the first pass of it. The easiest thing to do is add some amount of, like, the burst you send has some data in it that validates it. And so it's not outlandishly difficult to resolve. It's just not anything that's, it's not a problem we expect to see for a while, so it wasn't high on our laundry list, but it's easily solvable.
Cool. So the second question is, I'm curious why you didn't consider doing a power cycling, where, say, like in the middle of the night, you turn on the base station once every 20 minutes for a minute and a half and let people just, catch the signal then, since they have this domain knowledge.
We thought about that. That was actually one of the earlier designs. My work in Uganda signaled to me that the reason that people really want these towers is for emergency services. And so it's not necessarily that it's even going to be used. It's just the idea that we could use it if we wanted to. And that power cycling doesn't give you that property. I mean, obviously there's maybe we only have to wait an hour to call the ambulance or whatever. It's better than what they have now. But part of the goal of this was to be able to enable that I want to communicate right now situation.
Thanks so much.
Daniel Turner, UCSD. Great talk. Learned about something totally new. But an economic question, which is this the kind of thing that a government has to sponsor, or can you actually attempt to earn your money back based on plans? Because I know my iPhone plan will pay this pretty quickly, but I suspect people out there aren't paying what I'm paying for service.
It's a very complicated question. That's it. Now we're rolling into policy and legality and these sort of questions of what sort of network you can run. Obviously, GSM is licensed spectrum. And so having a rural entrepreneur run a station requires policy changes. There's been law changes, I believe, in Finland or Sweden right now, which is that it's legal to run a base station under 100 milliwatts. I've had talks with the CEO of Indosat in Indonesia about moving. It's difficult. It's a huge bag of worms, a cup of worms. I don't know. My English got really bad recently. It's a problem. And so it's a long discussion. It's something that we are really aspiring to, because the thing about Papua, where we were, internet was there and cell phones weren't. And the reason why is because you can just install a VSAT, and you can't just install a cell phone tower, and we want to have that model. So it's part of the point of this technology is to start to push on those questions and have reasons why these laws need to change.
Oh, okay. Thank you very much.